This video will be about integration and when we get an answer that would be a natural log or e to some power. Okay, with our first example, we're going to see what happens when we try to integrate problems that looks like this. Now, just like our previous problems, we will move this constant value to the outside, and we have 4 times the integral of 1 over x dx. Now, for instance, if we went through our rewriting, and this is not how you do the problem, but this is why you do the problem the way it does. If we go back and we rewrite this to be x to the negative 1 dx, and we follow our antiderivative rules, notice that we're going to get something that's undefined. We get x to the 0 over 0, or 1 over 0, which is undefined. But the answer to this particular integral is not undefined. What we need to remember is that when we took the derivative of the natural log of x, we ended up with 1 over x. So it stands to reason when we integrate something of the form 1 over x dx, we should get the natural log back. And we're going to say of absolute value of x. So here, with this problem, if we remember these things, then notice we end up with 4 times the natural log, the absolute value of x, and then plus c. So let's see how this applies throughout these different problems. Now, number 2, it looks like the same type of problem, but in this situation, we're going to have to replace this 5x minus 2 because it's not really in the form of 1 over x yet. So we're going to have to do a u substitution. So we're going to say u equals 5x minus 2. And just like before, we would have to go ahead and find du, which is going to be 5 dx. And so we're going to rewrite our integral. It's going to be 1 over u du. And again, du has a value of 5 dx, but we only have 1 dx, so we're going to have to multiply by 1/5 to make sure we maintain the value. And so we end up with 1/5 times the natural log, the absolute value of 5x minus 2 plus c. Okay, moving on to the next problem. Same situation again here, and it looks like we're really going to combine a couple of situations because we can move the numerator out to the front, and then we can also do a u substitution. Now, something to notice here, we do have a common factor, so we could factor that out, or we could just wait and build that into the value of du. Either way should be fine. If we keep with our way that we've been doing, we would have 4 times 1 over 3 minus 6x dx. And again, we want that 1 over x format, so we're going to let u equal 3 minus 6x. So du is negative 6 dx. And just like with the previous problems, we're going to have to balance this value. We already had a 4 out front, so times negative 1 over 6, and then the integral of 1 over u du. And again, simplifying some of this, and I wouldn't worry about simplifying just a tremendous amount, but this out front is going to be negative 2/3, and if I integrate 1 over u, all of that changes to the natural log, absolute value of what u was, 3 minus 6x, and then plus c. Okay, moving on to the next example. And again, the process is really the same over and over. Again, we can move 7 out to the front. And we do have x over x squared minus 4 dx. Now, be careful, you can't cancel the x in the numerator with the x squared in the denominator. But since this is an x squared, I would go ahead with our u substitution just to see what works out. And notice that du is going to be 2x dx. So this x here is found up here, so we don't have to worry about having that extra variable. So now we're going to have 7 times the integral, and we're going to have our 1 over u du, and then let's check and see if the value of du was 2x dx, but notice we only had x dx, so I'm going to have to multiply by a half out here to maintain the value. And now we're ready for our answer. So we have 7/2 natural log absolute value of x squared minus 4 and then plus c. Okay, for our next problem, and again it's the same process here, so we do have a little bit of rewriting to do. So in the denominator we do have 16 minus x squared, and we're raising this to the 1/2 dx, and then we will go ahead and let u be 16 minus x squared, and then du is going to be negative 2x dx, and again we are going to fill in what we know. That's going to be u to the 1/2 and then du. And then notice here let's go ahead and check our value of du. Du is negative 2x dx. We have x dx, so we need to multiply by a negative 1/2 to cancel that. Now notice this is not 1 over x. This is 1 over x, so to speak, to the 1/2 power. So we have to be careful. This is trying to trick us. It looks like it would be a natural log, but it's really not. This is going to be u to the negative 1/2 du, and if we go through our integration process, notice that's going to be u to the positive 1/2 divided by a half plus c. And so let's see what our final answer will end up being. We're going to have negative u, but u was 16 minus x squared, and all of that's raised to the positive 1/2 and then plus c. Okay, and again this problem looks like it might be a natural log problem, but we're not sure until we start working on the problem. And again, we do need to rewrite this, and we are going to have 2x minus 1 to the negative 1/3 dx. We do need to do a u substitution here. Let u equal 2x minus 1. Du is going to be 2 dx. And so it looks like we need to balance with a half. And then the integral of u to the negative 1/3 du. And now notice again, this is not 1 over x situation. This is 1 over the cube root of u. So definitely don't need natural log here. So we're going to have 1/2 times, and that's going to be u to the 2/3. So this is going to be 3/2 as a coefficient plus c. And here it looks like we get negative 3/4 times, and u was originally 2x minus 1 to the 2/3, and then plus c. Okay, now with these problems, looks strange, but again, notice earlier in the starting of our integration problems, we always, when we were choosing u, we would let u be usually the stuff that had an exponent. So let's see what we end up here, and it might be useful to rewrite this so that we see that this really is 1 over x times the natural log of x raised to the 4th power dx. And that's going to help us see why letting u be the natural log of x is going to be pretty useful. Because if u is the natural log of x, then du is really going to be just 1 over x dx, which works out great because that's all this extra stuff up here. And so really this problem is just a matter of integrating u to the fourth du, which is going to give us u to the fifth over 5 plus c, and then we do need to go back and fill in what u was to begin with. So we're going to have the natural log of x all raised to the fifth over 5, or 1/5 times this, plus c. Okay, moving on to number 8. This is a great example of a problem where we might have to divide up what we're given. I'm going to try to keep these separated as much as possible. So here we're going to have x squared over x. So that's just going to leave me with x, and then minus, and then 2x over x. That's just going to leave me with 2. And then we have plus 1 over x. And then, of course, dx. So when we start integrating, we can integrate each individual term because we are just adding and subtracting. So if I integrate x, I get x squared over 2, or 1/2 x squared. If I integrate 2, I get 2x plus, and again, if I integrate 1 over x, I get natural log, the absolute value of x, and then plus c. So this problem turned out to be a lot easier than it appeared to be. Okay, now let's talk about some trig in this. And when we integrate tangent x, we are so tempted to say that that is secant squared x, but it is not. We have to be careful. And let's think about this. Tangent x is really the same thing as sine over cosine, which is sine x times 1 over cosine x dx. It's a good way to think about tangent x. And so when we do a u substitution, let's see what we get if we let u be cosine x. So then du is going to be negative sine x dx, which then, well, that's good because sine x dx is what I have up here. I do have an extra negative, so I'm going to put the negative out front. And then I'm really integrating just 1 over u du. And now we know what that's going to give us. So we have negative, and then we have the natural log, absolute value of what u was, which was cosine x, and then plus c. Now sometimes you see this written differently because of that negative out front. Technically, you could bring the negative up to the front and make that cosine of x to the negative 1, which is going to give you the natural log of secant. So these two ways you could see this answer written, and it's about the same amount each time. So be careful and be aware that you could see both of those as a solution. Okay, and so this problem is going to be very similar to the one we just worked out, and it does require us to do some rewriting. And I would change cotangent to be cotangent's cosine over sine, so cosine 3x times 1 over sine 3x, of course our dx. And again, we'll need to do a u sub here. So I would let u be sine 3x. And so du is going to be 3 cosine 3x. Okay. And now what we can do is go ahead and integrate. And notice we have an extra 3 here. So I have 1/3 times the integral of 1 over u du. And again, that's going to be 1/3 times the natural log, the absolute value of what u was, which was sine of 3x, and then plus c. So again, that wasn't just terrible. It was different, but not terrible. Okay, and for the last ones, right, and again, another strange looking problem, but it is going to be pretty straightforward, more so than what you would think. Notice all this in the denominator. Now we can't divide up this and put it over cosine over 2 plus cosine over sine. That's a common mistake students do. And really, the only thing really left here that kind of makes sense to do would be a u substitution for the denominator. So I have 2 plus sine x, so du, and notice when I do the derivative over here, I'm just going to get cosine x dx. So that works out a lot better than what we thought it was going to, because here's my cosine x dx, and that's what we found with our du. So really we have 1 over u du. And again, when we integrate this, we know we're going to get natural log, absolute value, 2 plus sine x, and then plus c. Okay, moving on to our last example. And again, we have 1 over cosine squared, or 1 over cosine squared tangent x. Well, again, kind of the same idea. Let's break this apart and see what we can do with it. All right, and for this one's going to be kind of tricky. We have to remember what the derivative, and what's giving this problem away is that cosine squared x. We have to remember when we take the derivative of the tangent of x, we get secant squared. And secant, oh, miswrote that, didn't I? Let me fix that. Secant squared x. And so we have to remember that in this process, because 1 over cosine squared x is secant squared x. So in looking at this, I would go ahead and divide it up. And so we have 1 over cosine squared x times 1 over tangent x dx. And then go ahead and let u be equal to tangent x. And so du is going to be secant squared x dx. And that's going to be, all of this will take care of that 1 over cosine squared. So now when we do our integral, we're going to have 1 over u du, and inside that du is secant squared x dx, which is here and here. So that's already accounted for. So this entire problem really turned into a straightforward u substitution and an answer of the natural log, absolute value of what we let u be, which is tangent x, and then plus c.